Okay, so the domain is the set of all inputs. Again, the key word here, well, there's a couple of keywords, but remembering that when we identify a domain or a range, we're talking about a set of numbers. So, whoops, that's not what I wanted. I wanted my highlighter. And one of the ways that we talk about sets, and one of the easy notations that we're going to be using here is to use interval notations to talk about the set of inputs that defines this function right here. And then what are the set of outputs that we get once we put in each one of those inputs. Now, it's a little, let me see if you see here on my graph, do you see this kind of light green color here? You know, of course, you can't see it on yours. It's black and white. And you see sort of this bluish gray color here. So what that represents is, and do you see how they've got the little staples here? So they're actually like kind of superimposing the interval notation directly on the graph. So what they're saying here is, if I'm looking for where this graph begins and ends, it has a definite beginning point and a definite end point. And how do I know that? How do I know it has a beginning and an end? The staples down here definitely tell me that, right? And how about from looking at the graph itself? Kate? Okay. Right. What are these 2 points included? Yes. And how do you know that, Will? All right. What if I didn't have the brackets there and I just had the graph? Would you know if those points were included? You wouldn't know. Does anybody know if they're included, Caitlin? Because the dots are filled in, just like when we do the number line, right? We put a solid dot if we want to include that endpoint. So yeah, so our domain for this particular function, even though we don't have numbers along our horizontal axis, they would be all the numbers that start right here below this point, and they go to this endpoint here. And again, you have your staples because they're solid dots. Similarly, the output, you look for like the smallest value output and the highest. So you come right over here, and here's your lowest value of the output, and here's your maximum value. And so that would be the range. Again, this is sort of theoretical. You're looking at it, no numbers, so we can't write the actual interval down for the domain and range. So one of my colleagues, Ian Winokur, did this. How do I wanted to erase this. Hide domain and I guess I just have to close it and call it, it's ruining all the, I know it was ruining all the, now I got to go get it again. I should have cleared it out before class started. It's really cool. It's an animation. That's why I like it. So let me go back in and grab it for you. There it is. Okay, so I think this visual really helps with recalling what domain and range is. And so here's a function. Now here, notice you see like teeny little open circles. That's just because that's what this particular software does. Those really are filled in. So each of those are filled in. So don't see the open circle, see a closed circle there and there. Okay. So this function, could I use just one interval to describe the domain of this function? Why not, Katie? They have two definite beginning and two definite ending points. It's separated, right? It's not continuous in the sense that if I started here and I tried to trace this with my pencil or pen, I'd have to lift it off and then come down here to trace. So it's two separate domains that have to be joined together to describe the domain for this function. Okay, so here's a nice visual for you to see the domain of this function. Is that cool or is that cool? You know, it just comes straight down from here and then down, down, down. And then because this part of the graph is below the x-axis, it comes up, okay? And if I click my range, we go that way, cool, right? And then if I say hide domain and range, notice here I'm left along my y-axis with this nice green interval. And I don't know what happened to my pink interval, but let's put it in here. It would go from there to there, and then it would go from here to there. So you can see the domain and the range. Whoops, that's supposed to be green. From just looking at where the animation took us for both the output and the input values. Okay. So if I were to describe the domain here, I'd say I start at 2 and I end at 6. And then I pick up the function again at what x value? 7. And I go up to 15, and then I stop, and then I put my union symbol between them. Okay, because it's both of those sets, both of those intervals that define my whole domain. Right? So how about the range? What do we get for the range? Someone want to help me with the range? Now I'm going to be describing my output values. Caitlin? Yeah. Do we stop at 2? Well, let me erase. Oh, I can't erase it now that I've done it. Oh, here it is. Just let's see how it's, see how it's a little bit above 2, right? All right, so what would, you can just estimate. 2.3, and what do I put around those 2 values? Staples, okay. Someone else now for the remainder of the range? 4 and 6, and what do I put in between? The union symbol, right? Yep. No, you would, so if there was a connection here, like something like that, let's connect it with a straight line. You really have to hit that thing. So let's say it's not vertical, it's got a little slant to it. If it looked like that, then you would say the domain would go from 2 to 15, because it would be defined. You could actually trace it without lifting your pencil. It's only when you have to pick it up and start all over again that you're going to be looking at more than one interval. Good question. Anything else? Okay, so let's take a look at this picture here and see how we do together, and then you'll have a chance on your own. So here's a picture of a function. We say we would call this the graph of f, just to give you some language, the graph of f. And I know it's the graph of f because I see here y is the same thing as the notation f of x. So I know I'm using the letter f to describe this function. And so to find the domain, we just look along our horizontal axis, right? See what our inputs are, and then we use interval notation to describe it. So does someone want to give me a guess as to what you think the domain would be for this picture right here, this function? Isabel's said something. Andy, have you had a chance yet? Okay. The bracket -7. Yeah. Perfect. Yep. Because we go all the way to the left, we see that this starts at -7. I'm going to put my bracket right there at -7, and I have no gaps in this function, no holes, no jumps. It just keeps going and going and going and going and going and going forever and ever, because this arrow here tells me I keep going forever and ever and ever. So my domain starts at -7, but it goes all the way out to positive infinity. Okay. What about my range? We'll put that in blue. What about my range? Can you help me with that, Nick? Yeah. Yeah, because here's my smallest y value. I put my bracket like that. Yeah, it would be. Because look, ever and ever, right up the y-axis, okay? All right, so you can imagine the animation here, like you can imagine your lines coming down to your x-axis like that animation, your arrows, and then coming up from below. So you can imagine the animation you just saw, and that helps you to determine the domain, and then of course for the range, you'd be going this way, right? Your animation. So at your seats, I'd like you to identify the domain and range of each of these functions. Make sure you check with your table mates after you're done, and then put up your flag when your table all agree and you've reached consensus. And so we got consensus. Everybody came up and wrote what they thought was a domain and range from each of their tables. Overall, everybody's in agreement. Here's the tricky one right here. That's the tricky one. That's the one that a lot of people, if they make a mistake on this, that tends to be where it is. Any questions at all before we move along? Yep, Chris? What mistake tends to be made is that people they look at the X value a lot. I don't know why for this particular one, Chris, but people say -4 to negative infinity. I don't know why. They just pick out the X value instead of the 0 here. And sometimes they reverse the order. We always have to put the smallest number first and the largest number second on that interval. So, and since infinity is a concept, that will either be to the right or the negative infinity to the left. That's typically what I see, Chris. But I'm glad nobody has a question. That's fine. All right, so this is not new stuff. This is old stuff revisited, but it's a new name. It's new vocabulary for some of you. So if we look at this graph, notice what would be the domain for this graph, even though I didn't ask you. What's the domain for this particular graph? Negative infinity to positive infinity. And the way you know that is that this graph has two arrows, right? So that this graph, I could extend this x-axis all the way to negative infinity in the left direction. So I can go all the way out and I could come down and I'd find a value, and same thing here. This is a graph of a polynomial function, which we'll be studying next week. And the neat thing about polynomial functions is you don't have to think too much about the domain, because the domain, there's no restrictions on the domain. So think about a straight line. Put any value of x in. Think about a quadratic function, a parabola, any x in. So this is, the domain here is the set of all real numbers, so negative infinity to infinity. If you want, you can say all real numbers. You could write it out for me, that's fine. What about the range? What would be the range on this? Someone other than, let's see, who said, Will, Andy, Caitlin have spoken up today. Christopher, Nick, who else? Isabel, Katie, Liza, what's the range? Negative infinity to 3. And what do I do after the 3? Bracket. Okay. So let's take a look at this notation, f of 0. So if I were writing coordinates for a point on the graph, it says find f of 0. Where would the 0 go? Would it be what we typically call the x value, or would it be the y value, the output? Where would the 0 go from looking at this notation? And how do you know? Yeah, which one of these is 0, the x value or the y value? X, right, because as Jesse says, I've defined up here y equals f of x. X is the input, and my input here is 0. So yep, there's 0, and its corresponding output we could write as f of 0, but I'd like to know what is the value of f of 0, so I want to be even more specific. What is the value of my function when x is 0? What is the value of my function when x is 0? See someone going like this. Agree? Everybody agree? Okay. Right here? That's f of 3 is the same thing as f of 0. That's what we call our y-intercept, right? When x is 0, we go up and down the y-axis and we say, oh, if we find a point, we say, great, that's my y-intercept. Great. Now this one asks a little different question. Notice it says, for what values, it should have value of values. The reason it's plural is we're speaking about this function in particular. For what values of x is f of x equal to 0? So now where does the 0 go? The y value. So now we peruse along the x-axis and we see where our function crosses our x-axis, because when it crosses the x-axis, our value of our function is 0. We see it occurs at 2 places. So to answer this question, it says, for what values of x? So I say, when x is -3 and when x is 2. Those are the values of x that make this function 0. Isabel? Yes. Yep. Yep, that's fine. You could even put a semicolon in there if you want. I don't care what you put in there. You could say and, I don't care. What was the other comment? Yeah, whatever. Okay, so so this notation, we're used to saying x-intercept, y-intercept, and you need to become familiar with this so that hopefully you don't have to think about it all the time. When you see f of 0, hopefully you know you're looking for your y-intercept. When you see the output is 0, you're saying, I'm looking along my x-intercept. The new terminology that's used for functions is this terminology right here. We say that the values, x equal -2 and x equals 2 and x equals -3 are the zeros of the function. And if you recall, when I was using my graphing calculator and I was trying to find where my graph intersected the x-axis, I went to that menu that said 0, and I said, we'll come back to this in a couple of weeks. So we don't use x-intercepts anymore. You don't see x-intercepts on your graphing calculator. You see the word 0, and that's when your function, the value of your function is 0. So it's the same as what we've been traditionally calling x-intercepts. Okay, so by definition of a function, each value of x can have at most one value of y. So how many x-intercepts can we have and how many y-intercepts can we have? So anybody want to take on either one of those questions and explain why? Isabel? So Isabel's claiming that you can only have one y-intercept, and why is that? No pun intended. Right, so we know our input, our domain, when we're looking for our y-intercept, the input is called 0. And that can go to only one value, can only have one output value called f of 0. If it went to somewhere else, remember when we did our vertical line test, if for some reason we had another y-intercept there, that wouldn't be a function because it would fail the vertical line test. Okay, so that's correct, Isabel. That's good, even a good explanation. How about for x-intercepts? Katie? As many as you want, there's no limit, okay? Because all our x-intercepts have, regardless of however many you have over here, x1, x2, x3, x4, they're all going to one unique output called 0 to be a x-intercept, okay? So yes, there is no restrictions on the number of x-intercepts, but there is a restriction because of the way we define what a function is. Okay, now this next thing is, I think, a fairly intuitive idea, and I like the way your book approaches this. Your book has this little story about someone having a fever because they have the flu over time. It's on page 229 and 230 in your book, and I think it kind of takes away from the kind of the scariness of looking at the definition of increasing, decreasing, and constant intervals when you just look at the algebraic definitions. You get a feel for this. So here's a story, and the story goes like this. You woke up at 8 o'clock, and you were thinking, oh, I've got to get to my math class, and you recognized that you had 101 temperature. Well, you said, okay, I'm going to stay home and get some rest. And 3 hours later, you were feeling better. So you said, okay, I missed my math class. So not to make things worse, I'm going to go to GCC and go to my English class. And while you're at your English class for 2 hours, your temperature starts going up again. You say, oh, crap, I guess I wasn't really done healing. So you go back home or you go lay in the studio, and for the next 2 hours, your temperature stays the same. All right. So I just make the story up, right? Could be any story that follows that picture. Every graph has a story, so to speak. All right. So when we define intervals where our function is increasing, decreasing, or staying constant, we always use an open interval. That's the key for this book. Now, you may pick up another book and they may say it's closed, but for our book, when you define the interval, it's always open. Right? And so how would we find a decreasing interval? I don't think anybody would disagree with me that this first picture is a decreasing interval. It's very intuitive. And it means as you move from left to right, as your x values get bigger, your y values or the graph of your function is dropping as you move left to right. That's pretty intuitive, I think. Does everybody agree with me? Yeah, right. Then at the point 3 hours after 8 o'clock, as you continue to move left to right, your graph starts to increase. So we say that this interval is where our graph is increasing. And then 5 hours after 8, oh, what would that be? 5 hours after 8, 1 o'clock in the afternoon, from 1 to 3, our temperature staying exactly the same. We call that a constant interval. Okay, so the only thing we need to learn how to write is how do we express these intervals where this function is decreasing, increasing, and constant. Now here's the key. Not only is it open, so you'll only see parentheses every time you write an open, a decreasing, or a increasing, or a constant function. So you always use parentheses. But to describe the interval, it's always your input values only. Whatever your x values are, or whatever your independent variable is, that's what goes inside those parentheses. It's always expressed over your variable that you use in your domain. So you're not going to be looking at the temperatures like 101 to 98.6. You're going to say this decreasing interval starts at 0 hours after 8 a.m., which is 0. And it goes to 11 o'clock, which we say is 3, based on our definition of our independent variable. Okay. So what would the open interval be for the temperature that's increasing? Can you help me with that, Drew? Yeah. Yeah. Yep. Perfect. And what about constant? Sam, can you help me with that? 5 to 7. See, nothing to sweat about, right? Very intuitive. Am I assuming too much by saying it's intuitive? Does that feel fairly straightforward? Okay. Okay, so at what time is your temperature the lowest? What time is your temperature the lowest? 11 o'clock. Which 11 o'clock? Which one, AM or PM? AM. Okay, because Jesse went right there and noticed in these last two graphs here that the lowest temperature occurred at 11 a.m. and it was 98.6. So let's do this one more time. I did it after you handed in your first project. I'm going to do it one more time because some of you still need help with this. If I ask you to tell me or interpret what these coordinates mean with a sentence or two, you write down the coordinates. It always helps if you put the units in, and this one is hours after 8 a.m., comma, 98.6 degrees Fahrenheit. If you do that, your sentence is written for you. This point, to interpret this point or to describe what the coordinates of this point means in a sentence, I would say at 11 a.m., my temperature was 98.6 degrees Fahrenheit. It's that simple. Notice each of these numbers appear in the sentence in each of the units. Now you might say, I don't see 11 anywhere, but we've interpreted what 3 means by the definition of X, which is the number of hours after 8 a.m. You could have also said 3 hours after 8 a.m. instead of putting 11 a.m. in. Okay, so this is how you would interpret it. The next picture here shows you sort of the precise algebraic way to define increasing and decreasing. You read that over, it's in your textbook. It's exactly what we just did, but it looks a little scarier because there's no numbers. It's all in terms of x1s and y1s and f of x1s and f of x2s. Okay, so I want to come back here and take a little picture of something. So let's take this picture right here, this graph. And let's cut it, and let's go over here. I'm just going to put it in here for later. I don't know why I get all those lines with my little camera. If anybody knows or can figure that out, I'd appreciate it. All right. So this language, we spent a lot of time in my first class talking about this language, relative maxima and relative minima. So let's read it first. Want to read it for us, Ryan? Oop, typo. Blah, 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 right? A lot of language, a lot of new terminology. What's it mean? Well, what is maxima and minima? Do you go around talking about maxima and minima? What's the MA? What does that mean? Here we're talking about maximum and minimum, and up here we got maxima and minima. Why does it go from mum to ma? Plural, right? That's how you would represent the plural. The plural of maximum is minima. I mean maxima, and the plural of minimum is minima. Couldn't you say maximums and minimums? Is that allowed? Yeah, but this is what they say in mathematics. All right. Relative means that we're looking at the highest point or the lowest point in a neighborhood. Your graph has to be increasing and then decrease right around that point. You have to have something on both sides of your point. In other words, if I had a graph that looked like this, and let's say that point was C comma F of C, and this point was D comma F of D, you couldn't say that this was this point F of C, you could not say it's a relative maxima because there's nothing on the other side of this. I don't know if when X is less than 0, if this graph was coming down like this, and if it was, then I'm not going from increasing to decreasing. I could have been like this. I don't know. So your graph has to be defined on either side of that point. You have to be able to see what the values are prior to that point and after. So I always think about just kind of putting a little teeny circle over that point or near that point and just saying, hey, am I the king of the mountain here in this neighborhood? Absolutely. That makes me a relative maxima. And you'd say, well, why do they use the word relative? Because in this particular graph, I can say f of c, the output value, is the absolute maximum because this continues to go down like this. But some graphs you'll have multiple points, peaks and valleys. So they say relative because it's relative between two on an interval. And similarly over here, if I just put a little circle right around there, you notice that f of c, the value at the point C, is the lowest point over that interval. Wherever you define that interval to be, you could say it's C1 to C4. So over that interval, f of c is the smallest value in that neighborhood. Okay, you just look on either side of it. So someone in my class asked a question in the first class that I thought was a good question. So you can see in this situation that you have several relative maxima values and several relative minima values. So let's suppose I said this point was at 20, negative 420, and this point was at 330, and this point was at 8, negative 40, okay? And this point was at negative 2, negative 35, okay? So if I said to you, what are the relative minima values? What are the values of the relative minima? I can't spell it. Minima. Okay? All I'm interested in is what are my smallest output values? That's all you list. So what are my smallest output values within a certain neighborhood? Well, here's one right here. I'm only interested in that number, the output. Where's my other one? Right here. I'm only interested in that value, my output. Those are my two relative minima values. Where are my relative maxima values? Maxima, okay? 20 and 30, right. Okay. And that's because if I were looking at this graph here that we just looked at a minute ago with our flu scenario, and I wanted to know where, what your lowest temperature was, which I asked you, you didn't have any problem saying 98.6. I'm not really that concerned about where it occurred or at what time. I just want to know, when did you reach normal? What was your lowest temperature here? In this case, it was 98.6 on this interval right here. Okay, so I'm going to give you 5, 10, maybe like 15 minutes or so to work on this. And then I'm going to call you back together because we have another big idea to talk about called even and odd functions. But I want to give you a little bit of a break to try working on all of this new information that you've just sat through and we work through together. And then we'll come back. So at 25 of, I'll call you back together. Okay, the first thing hopefully you notice about this function is the domain is all real numbers because you see either end of the function has arrows on it. So it's all real numbers, and you can express that as either writing all real numbers, or if I ask you to use interval notation, if I specify that, then you say negative infinity to infinity. Where applicable, use interval notation. Very good. Range, what do we have for that? Range. Negative infinity to 4, and then what do I put at the 4? Brackets, right. It's definitely defined on your graph because there's a solid point right there. Okay? Now this is the tricky part, the difference, and it's a technical thing. When they ask you for the zeros of f, what they're saying are, what are the x values that make this function equal to 0? So you don't list x-intercept coordinates. You just say what the zeros are. What are the x values? That's all they want. So what are the x values where your function is 0 here? What you have for that, William? Oh, did you already put it away? Oh, okay. X is equal to 1. Okay. Yeah. Yeah. Okay, -4 and 4. Good, right? So you just give your x values. F of 0 says, tell me the y value when x is 0. And what do we have for that, Sean? Did you say 10 minutes early or 15? Okay. Where are you? Here you are. Have fun at your rally. Okay, now intervals on which f is increasing. So probably before all of this in your notes, when you see intervals where a function's increasing or decreasing, you should probably put in the word open to remind yourself that we're looking at parentheses, they're open, and we're only looking at the x values or whatever your horizontal variable is. So what are the open intervals for which this function is increasing? So you say, oh, as I move from left, and where's my left here? My left is -infinity. As I move left to right, my function's increasing, increasing, increasing until I get to -2, and then I start to decrease. So -infinity to 2, open interval. Then at, -2, sorry. Then at -2 to 0, I'm decreasing as I move left to right. So I'm going to start that. I'm just going to go like in order here. So -infinity to -2, I'm increasing. -2 to 0, I'm decreasing. And then what happens at 0? 0 to where? Let's see. 0 to 3, I am increasing. And then from 3 to infinity, I am decreasing. It's just how your author has chosen to define. Who asked that, Nick or Brian? Brian. It's just how this particular author has chosen to define increasing, decreasing, and constant intervals. So another book like the book we used to use before this, the guy insisted on brackets. It's arbitrary. Values of x for which f of x is greater than or equal to 0. So if you're looking at this graph, what does that mean? What does that notation mean? Just from looking at the graph, the values of x for which f of x is greater than or equal to 0. Isabel? So if we're looking at the, right, so it's either sitting right on the x-axis or it's above it, right? So what are the values of x that this graph is either sitting on the x-axis or it's above it? Katie? -4 to 4. And what do I put around -4 and 4? Parentheses? Staples, brackets, right. Okay, if I didn't have that little greater than or equal to, if I just had greater than 0, I'd have parentheses there. Right? All right, and this is just the language these books use, and it's any relative maxima and the numbers at which they occur. You really need two sentences here because you have two relative maximas. You have a relative maxima is where it's at 4, and it occurs at what? -2, right? It occurs at x equals -2, but the relative maxima value is 4. And then you'd say it again. Well, I have another one. Where's my other one? Oops. Let's see. My other one occurs right here. My relative maxima value for this function is 2, and it occurs what? And where does it occur? At x equals 3. Yep. Any relative minima in the numbers? Do we have a relative minima here? Yep, right there. My relative minima value, or relative minimum, since I only have one here, is 1, and it occurs at x equals 0. Okay, so what do I do to find the values of x for which f of x is 3? What do I do up here on my graph to find that, the values of x? Someone help me? What would I do to find the values of x other than Katie? Anybody? Nobody got the answer here other than, huh? I don't know. I've scrolled up. I can't scroll back down. The values of x for which f of x is 3. How do I show all the spots where f of x is 3? What could I draw? Eliza? I can graph a line at y equals 3, right? Which is a horizontal line like this. That's the same as y equals 3, and y is the same as f of x. So this is the same as y equals f of x, which is 3. It's a horizontal line straight through y equals 3, or f of x equals 3. And then you come down to see, well, is it right at -3? I don't know. It's either -3, where else? A little bit bigger than -1. Maybe it's right at those values. Anywhere else does it hit? So maybe it's -3 and -1, or a little bit on either side of that. It's fine. So the x values are -3 and -1. Final question, is f of 5 positive or negative? So do I look at the number 5 to determine that? Jesse's saying no. Where do I look, Jesse? I look at the 5 on the x-axis, and then where do I go? Go to the where? Just go down. So I just draw a vertical line straight down through, and I would intersect my graph. Would I be above or below the axis there, Jesse? Below. So f of 5 is negative. So you would write that like this: f of 5 is less than 0. It's negative. Okay? Or you could circle negative. Whatever floats your boat. Okay? Any questions on that? Okay, so even and odd functions are easier to see from their graphs than they are to define algebraically. So we call this first graph that you have on number 9. We say that this graph is an even function or has even symmetry. And what we mean by even symmetry is if I were to fold this graph right along the y-axis, for each point on the right-hand side, there would be a corresponding or point that is reflected on the left-hand side. That's the same distance away from your y-axis and the same distance above your x-axis. So in other words, let me see what this would look like if I could animate it just a little bit or interact with it. So let me come down here. Now, where did I put this? Here, is it here? No, is it here? No, it's supposed to be here. Oh, it's because I went in. Oh, it's this graph right here. My multimedia library. You have this in your book, and you have all these things available to you. I don't know if you know that. So let me open up so I can get the same values that you have. I'm going to do a little interactive. So here's the function that's being graphed, x to the 4th minus 10x squared plus 9. Okay, and what's the first point we're looking at? We got 2 points we're going to look at according to the table in your book. X equals positive 2.5 and x equals negative 2.5. Well, first of all, let's just look at this graph and see what's going on as I move. Okay, so I'm moving along this graph. I don't know if I can get exactly to negative 2.5. I don't know why I picked negative 2.5. I can't even get there. I don't know. This is, well, let's just fill in the table with some of the numbers we have available right here. So what do we have here? X, the opposite of X, these are our 2 inputs, and then the output. Okay, output values. So here we are. Here's 2 input values, 2.91 and its opposite. What's the output value? Can you see it? Negative 3.97. We have the same y value for opposite x values. Right? And if I folded that graph over the y-axis, these 2 points would lie right on top of each other. Right? It has a mirror reflection. Right? And you can see any point. Let's pick another point on this graph. Here, let's go down this way. Here we are. Can you see that? Any of this? Control what? Yeah. Yeah. Ooh. going the wrong way. I am moving the other way. Full screen. Uh-oh. Now we can't see anything. Huh? Oh, there we go. Oh, it's left click. Oh, yeah. Now Jesse said, yeah. After I got so little, I'd be blind. Okay. Thank you. All right. So there we go. So opposite values now. We have 0.62. It's opposite value. But what about the f of x value for both? 5.3. They're the same. So the way we say that mathematically, we can, there's a zillion points there, right? That's being real mathematical. There's an infinite number of x values here. We can't check them all. So if we have to determine if this has even symmetry, we have to show that f of the opposite of x is the same as f of x. So if I take an x value and I take its opposite, the y values, the outputs are exactly the same. So how do I do that? I go to my function. Here's my function. Here's f of x. F of x is x to the fourth minus 10x squared plus 9. And now I say, what is f of the opposite of x? And if they're the same, I know I have even symmetry for every single point in the domain. So where I see x, I replace it with the opposite of x. And if it comes out to be exactly the same as f of x, I'm golden. Well, remember, that's a little -1 in there. -1 times x is the same as dash x. So when I raise -1 to the fourth power, I raise x to the fourth power. Well, -1 to the fourth power is what? 1. -1 to the fourth is 1. Negative number to any even power is positive. So this is x to the fourth. This is minus 10x squared. And this is plus 9. Well, lo and behold, f of x is exactly the same as the f of opposite, f of the opposite of x for all x's. So you've just proven mathematically that this function is even. Okay, so that's how you would do it. You would put down your function, then you replace it with the opposite of x, and if they're the same, you're golden. It has symmetry about the y-axis. Okay, odd functions. Let's take a look at an odd function. Here's an odd function. Okay, and I think that's the same one you have, right? Okay, so now let's look at, you've got the first row filled in. So can I erase this? I can't. Where's my picture thing? Hang on, I want to get a picture of this. Here we go, and we'll put it on a separate screen. Oh no, then I won't be able to interact with it. Never mind. Go away. Okay. Well, let's see. Oh, I can't get rid of anything. All right. So I should have had two separate tabs up here. So this says x cubed plus 4x squared minus 4x minus 8. Let's see if I play around with this little picture, what happens with an x value, what's its y value, and then the opposite of x, what's its y value. So let's see. I'm just going to play a little bit here. So here we are. Let's see. Let's get 2 points. How about right there? So if you filled in your table, x is 1.85, its opposite is -1.85. Are their y values the same? No. Are they even opposite? Are they opposite? So this is neither. So whoever said neither is correct. How about this one? All right, look at this. Do we have opposite x values? -1.85 and 1.85? Yes? What about our f of x values? What are they? Opposite. This has symmetry about the origin. This is what we call an odd function. And the way we define an odd function is to say this. F of the opposite of x isn't equal to f of x. It's the opposite of f of x. So if you wanted to show that with this function, x to the fifth, let's keep the function here. F of x is x to the fifth minus 10x cubed plus 17x. Let's find f of the opposite of x. F of the opposite of x is this. The opposite of x to the fifth power minus 10 times the opposite of x to the third power plus 17 times the opposite of x. So this is the opposite of x to the fifth plus 10x cubed minus 17x. This is the opposite of every single one of those terms. So that shows you have odd symmetry, which means this is reflected about the origin, which means that these two distances right here are the same. Okay, so that's the end of section 2.2. I will give you your exams back now.